First of all, just in context, well, why bother to try and do all this research? It's very expensive and time-consuming, and the options, as we've heard, where you can wear contact lenses or you can have a corneal graft operation, and that's the end of it. But it's not. I mean, there are problems with contact lenses and surgery, and they've been talked about the methods, but we haven't really heard a lot about the complications, the intolerance, quality of life issues. So I think all of us would like to have better options in the future. And I think by identifying the causes of keratoconus would open the door to better developments. The next slide, please. I'm aware that a lot of this is complex, and I'll try and make this as accessible as I can for me. I'm a clinician rather than a scientist, and I work on the premise that if I can understand it, then anybody should be able to understand this. So up on the top here, what is keratoconus? And what we know about it is that it has differences from an unaffected cornea, and by looking at these different parameters or measurements, can this give us a clue as to what's happening in keratoconus? And so looking at these things here, these are routes that people have addressed to try and find out the underlying causes of keratoconus. So the biomechanics, so how does it behave? How bendy is it? Looking under a microscope, what does that tell us? Well, not very much. The cornea is thinner, but it otherwise looks normal under a microscope. Are there environmental changes which can be causing this, such as eye rubbing? Can we measure the enzymes? Take a piece of a donor cornea that's been donated for research and looking at what's happening at a cellular level and the enzymes in the tissue. Is there something there? Proteomics, that's a developing science where you look at all the proteins in that and compare it with somebody who doesn't have keratoconus. There are other clues in there. And then lastly here, which is my particular area of interest, is molecular genetics. Is there a message in the genes which can tell us what proteins are being controlled, which are different in people who have keratoconus than people who don't? So this is what happens in a gene. So in a very short summary, DNA, which is the code, that's the book that contains all the information, that message is transferred to RNA. That message is then transferred to make a protein, which is a long string of amino acids, and that's the collagen in the cornea and the enzymes. And then these go through a 3D folding configuration to form the functional proteins of the cornea. Outside of that, there are environmental influences, such as who we are, our ethnicity, our age, the presence of other diseases, such as allergy, which can influence this as well. So all disease is this combination between your genetic makeup and the environment that you live in. And this is the balance of the cause and effect. This has been a real problem in teasing out the causes of keratoconus is what's causing it and what's the effect of having it. And we'll go through that in a bit more detail in a moment. So next slide, please. What is keratoconus? This is of importance because working out any disease, it's really important that the definition is tight, that we're excluding things which look a bit like keratoconus, thinning or scarring or whatever, and we don't study them, but we strictly limit what we're investigating into true keratoconus. So basically it's bilateral, usually asymmetric thinning of the cornea. The cornea becomes thin. As a result of this, it causes short sight and astigmatism. So the cornea becomes more curved. The more curved the cornea, which is an important lens surface of the eye, then there's an increase in myopia, short sight, That is associated with astigmatism, which is irregular astigmatism, means there's no one curve which defines the shape of the cornea. Therefore, spectacles don't work very well, and hard contact lenses work better. There's a delayed onset of the changes, so people are maybe born with a tendency to develop keratoconus, but the signs don't normally develop until the teens or early 20s, and then there's a progression through till late 30s or 40s, and then stabilization, possibly or probably due to a natural cross-linking, as we've heard. So as we get older, all of our joints get stiffer, and the cornea similarly becomes stiffer, and so a natural cross-linking process. And cross-linking probably accelerates that event. And so the environment and genes both playing a role. Next slide. So these are cousins in the field of keratoconus, and there's Ken Pullum, who's kindly provided some of these slides. So this is a light section, cross-section taken with a slit of light of the cornea. And so the cornea is normally thicker in the periphery than in the center. And during the development of keratoconus, primarily the central part of the cornea becomes thinner, and then over time it tends to bulge forwards. There are variants of this, and so there is the apex cone here, where the ectasia, which is the term for protuberance, is mainly in the center of the cornea, can be drooped a bit lower below the visual axis, can be primarily at the bottom, which is a condition called pellucid marginal degeneration, or it can involve the whole cornea, which is very uncommon. So how these relate to each other, and whether they're all part of the same condition, and that the difference in the appearance is determined by environmental reasons, we don't know. But if you're doing any research, then you do need to identify the type of change that's happened. How all these changes relate to simple astigmatism, which is very common in the population, and loads of people with glasses have astigmatism, but they don't have keratoconus. How these two things relate, and how keratoconus relates to simple short sight, we don't know. But we do know it's important. As we've heard, it's a major cause of surgery, and this is again from the Australian Corneal Graft Registry. So about a third of patients who have corneal surgery are having corneal surgery for keratoconus. So it's important. So I keep harking to this point that it's important. If you're writing a grant to try and research keratoconus, a lot of the comeback is that it's not that important because it's not very common and there are good alternatives, contact lenses and surgery. And we've had to do our own studies for this to actually justify it, showing that there can be severe visual loss associated, severe permanent visual loss associated with keratoconus to justify our research. Next slide, please. So these are clinical variants. This is the light cross-section, a bit difficult to see, a bit dim, I'm afraid, but this is sort of normal, central cone with thinning primarily over the visual axis, which is roughly this line here, where the important rays of light getting to the back of the eye are travelling. Down the bottom is the thinning is pellucid marginal degeneration, and then thinning of the whole cornea in keratoglobus. Next slide, please. And so this is the diagram cross-section. Next slide. And so thinning occurring in the center. Next slide. Followed by protuberance or ectasia. Ectasia is a common word which is used to describe bulging of the cornea. Next slide, please. Complications can occur, as we've all aware of reading around this. And so these are the significant causes of ocular morbidity, of not being able to get on with your lives, and occasionally can lead to permanent sight loss. And so perhaps the most common, text off the bottom of the slide, I'm afraid, is acute corneal hydrops. As the cornea bulges forwards, it becomes so stretched that there is a split develops in the back layer, that's called the decimase layer of the cornea, and that allows fluid to enter rapidly, and so that can be uncomfortable or painful. A lot of sudden reduction in vision due to this grey edema of the centre of the cornea tends to improve over 3 to 4 months as the cornea scars. The cornea can flatten, and when it flattens, the vision can return to a large degree, but occasionally it can be associated with permanent scarring that can reduce permanently the quality of vision, and also the inflammation can be associated with blood vessels growing into the cornea, which could then jeopardize the risks of success of future corneal transplantation. Approximately 2% in a hospital-based practice like at Moorfields, maybe 2% of patients eventually will develop an acute corneal hydrops. With that. Next slide, please. How common is it? Not very good data, and a lot of the data is biased because we work within a hospital practice, and it takes no regard of optometric practice in the high street, so to speak. So what we know is mainly based on hospital-based practice. And the best study of this, so the bad studies, you look at a hospital with 500,000 patients and a few thousand keratoconus patients, that doesn't give a good idea as to how common it is. This is a study which was done in Denmark, and in hospital you code patients, they're all given a code, and one of the codes is for keratoconus, it's a numeric code, and they looked in the whole of Denmark as to how many patients had this code in hospital practices, and they came up with a figure of 4,600 cases, which if you extend to the population in the UK, equates to approximately 50,000 individuals would have keratoconus. This compares to probably 9 million individuals with myopia, and so a lot of funding is going towards short sight as opposed to keratoconus because it's more common, but some of this research into myopia is having a knock-on effect, and was briefly mentioned in the introduction, is having a positive knock-on effect to research into other conditions, including keratoconus. And so this is the figures, and so the prevalence is 86 per 100,000, or 1 in 1,600 individuals. So that's an indication as to how common it is in the population, and that's in the susceptible population, so you have to adjust the figures because individuals of 1 or 2 years of age won't be having it anyway. Next slide, please. The effects, what are the environmental things which are playing onto this, and what other things do we know increase the risk? Well, probably the strongest is that of ethnicity, so race. And if you look at a comparison between, so Asian here is actually South Asian as opposed to East Asian patients, that it's more, the prevalence is higher in South Asian patients, Pakistan, India, as opposed to white individuals, and this also is true of, probably this figure is similar for black patients as well compared to white patients, 4 times. So there is a strong ethnic bias towards that, and also this affects the age of presentation, so South Asian individuals would have an earlier age of developing the condition, and also a lower uptake of corneal surgery. And so there are, that may be sort of a cultural point as opposed to a genetic point. Next slide, please. So it's more common in black and South Asian individuals than white individuals, so there may be a genetic clue there. Making the diagnosis accurately, we say it's very important that we get the diagnosis right before studying genetic influences. And so the usual cases in textbooks, Munson's sign, so on and so forth, is now sort of being superseded by much more accurate methods of detecting early keratoconus. The importance of this is we got cross-linking, which is a potential intervention to treat very early cases before they get on to advanced disease where you have Munson's sign and poor vision. So it's a chance of intervening earlier. And so on top of this would be topography and identifying where they're so subtle that you're picking up other conditions where you think, well, maybe it is, maybe it isn't. And these terms such as keratoconus suspect, Form-Fruest disease are patients who are picked up with these very sensitive screening checks, which you may have seen in clinic, these colour maps, which are so sensitive and subtle that they're picking up cases we're not really sure what it is. And then clinical keratoconus. This is a genetic family tree, looking at cases where provided a result when they included these suspects, and the results was then disproved because keratoconus suspects don't necessarily ever develop keratoconus. These are the types of maps which you may see in clinic, and so repeated readings with computerized algorithms looking for progression of keratoconus for potential cross-linking. Next slide, please. Using a combination of techniques, you can increase the sensitivity of pickup of early changes. And so we looked at those colour maps, they're imaging techniques, but by also measuring elasticity of the cornea, the flexibility of the cornea, and then combining that with colour maps, you can push the sensitivity up in this direction. So you can make, by using different tests, you can increase the sensitivity of the measurements. And so how this works is a little puff of air distorts the cornea, it's similar to the test which optometrists do with the air puff to measure intraocular pressure. Similar to that, little puff of air distorts the cornea, and as it bounces back, it oscillates. And by measuring the way the cornea oscillates, you can measure the elasticity. In practical terms, by using this measurement, combining it with those colour maps, you can increase the sensitivity of picking up earlier changes. Why is that important? As I said, because we've now developing methods such as cross-linking, whereby very early changes can be intercepted and treated while there's still useful, unaided, or spectacle-corrected vision. In the future, from this genetic research, we hope that a genetic panel of genes, a small finger prick test, put on a strip, will identify genetically patients who are particularly at risk of developing keratoconus. That's where we hope this is all going to lead. Next slide, please. We talked about genetic background in terms of the ethnicity, race, also the important environmental factors. Atopy is a predisposition to allergic disease, such as eczema, hay fever, asthma, and so we know that atopy, which is the group of allergic conditions, is more common keratoconus is more common in patients who have severe allergic eye disease and patients with severe or allergies or allergic conjunctivitis tend to rub their eyes, and so is eye rubbing a risk factors for this, and could the inflammation caused by eye rubbing be releasing cytokines, which are enzymes into the tear film, which are sort of digesting the cornea? Well, it's possible, but I think that no one's ever going to be able to conduct a study on the role of eye rubbing in keratoconus. It's so difficult to quantify retrospectively, and I think it's never going to be more than a suspected risk factor for this. Next slide, please. Myopia is short sight, and so what's the relationship between keratoconus, where there's distortion and thinning of the cornea, and myopia, short sight, where the whole eye is enlarged or elongated, and there definitely is a relationship between the two. And so these are some measurements. This is a small group of individuals who not wearing glasses, and the length of the eyeball on average, measured by ultrasound, is 23.5 millimeters. And patients who have a group of patients who have keratoconus, who don't or do have a corneal graft, the similar measurements are longer. And so keratoconus is distortion of the cornea, but associated with that, the eye is globally bigger on average. Not in everybody, but on average it is. So in some way the eye is enlarged, and so this is linking, as I'm coming to in a moment, relevance to huge studies that are being performed to identify risk factors for short sight. Why is it so important? In Taiwan, at the turn of the last century, almost nobody wore glasses, and I understand that now 95% of women at age 25 are wearing spectacles. So some important change has occurred. It can't be a genetic change, but there must be something happening which is increasing the risk of becoming short-sighted, and stimulus for a lot of money being pushed into research into myopia, short sight, and part of the spin-off of this is clues into the etiology of keratoconus. Next slide, please. So structurally, what are the differences? Are there any clues here? Not many, unfortunately. And so this is on the front of the cornea, there's the iron ring, Fleisch's ring, so iron deposition. Looking under the light microscope, there's no difference. Looking with confocal microscopy, the nerves in a normal compared to a patient with keratoconus are different. They're more spaced out, but we don't really know whether this is cause or effect. The cornea is becoming more stretched, so the nerves may be becoming further, move further apart. Looking with electron microscopy and staining, these are the collagen fibers, these little round structures, and the ground substance between them, which holds them in a regular spacing. There are minor differences in the spacing and the structure and size of the keratoconus under the microscope, light microscope and electron microscope. Next slide, please. This is work from Keith Meek, who spent a long time, decades, researching this at Cardiff. I think he's strong links with the keratoconus group as well. And what he's looked at is moving beyond electron microscopy to look at the way the collagen fibers in the cornea are orientated. And so again, looking for clues to how the structure is different in people who do or don't have keratoconus. And so this is using X-rays shining through the cornea, which causes a scattering of light. And scattered light then forms a picture on a detecting plate. And so this is the same as in the news, identifying the structure of DNA with electrons. You get a pattern which gives a clue as to the spacing of the molecules. Next slide, please. And the outcome of all this is that there seems to be a slippage in the orientation of the molecules within the cornea. So they're moving apart. And this is the little bow tie effects which you get from, so each one of these little tiny patterns is one highly aligned shot of X-rays through the cornea and looking at the primary direction of the scatter. And it seems to be a change to form this circular pattern on the cornea. Next slide. Which is best explained by this process here, whereby this is the normal collagen fibers, each anchored to the next by these little attachment proteins, and that some way they're slipping apart. And so one fiber is moving relative to the next, and an easy explanation of how collagen cross-linking works is that it's forming some sort of bond between the two collagen fibers to prevent the slippage, but it's not proven exactly how collagen cross-linking is working, but that's an easy to understand analogy how it might be working. Next slide, please. So looking at the structure, it's really effect rather than cause, so we see the molecules moving. Looking at the other potential things, so looking at the enzymes working in the tissue or in the tear film, and a lot of studies have looked at this, and they found differences. And so there are these names given to these. A cytokine is something which is making cells do something, and so there are these molecules which guide cell processes, which are different in people with keratoconus compared to people who don't. But again, in summary, it's difficult to work out cause and effect. Is this an effect of the distortion and abnormality in the tear film as a result of the distorted cornea, or is it the cause of the distorted cornea? The biggest change here is SOD1, that's the name given to it, superoxide dismutase, and that's markedly increased. That's a free oxygen-free radical scavenger molecule, and that's highly different. But when you take that to family studies, it seems very rare in the population. This change here is very rare in the population with keratoconus, and doesn't explain in the majority of individuals the changes in the cornea. Looking at proteomics, that's this mechanism where you take all the proteins, and so hundreds, if not thousands, of different proteins in the cornea, and you compare them with individuals with and without, and there are differences, there are huge differences, and it's again hundreds of different proteins are all slightly changed, and working out which one is important is very difficult to derive. Next slide, please. The ones, again, looking at the TIMP is an agent which is an inhibitor of the natural digestive proteins in the cornea, so this is a potential mechanism. Is there some sort of auto-digesting process going on, whether collagen is through changes or disease is digesting itself and gradually becoming thinner, and so the molecules which block that are not changed, and so this is looking at target genes. Target mechanisms are the changes. Collagens, so collagen, there are numerous collagens in the body, and so looking at the ones in the cornea, there are changes or signals in some of these collagens, and apoptosis, which is the natural cell death, regulating mechanisms in the body. There is an association with filigrin, which is the strongest association with allergic eye disease. But looking at this one in populations with keratoconus, there's not a good link with that. So a lot of false starts have happened, I'm afraid. Next slide, please. So this is the example, briefly, this is superoxide dismutase. It's located, and so any explanation, you have to look at whether it's a reasonable explanation. And so this is the molecule which is the oxygen-free radical scavenger. It's located on chromosome 21, and there is an association between Down syndrome and keratoconus, so it's a reasonable candidate. It's highly expressed in some populations with keratoconus, but it was demonstrated to segregate in two families, i.e. the change was present in those with keratoconus, but not in those who don't have it. That's an important filtering step in working out cause and effect, that it's present in people with it, but absent in people who don't have it. And so a lot of excitement at this point, but then, as with so much of this, people look at it in more detail and find out that it doesn't actually hold water in the general population. So another false start. Slide, please. As you remember, on that very early on, we talked about DNA. The message goes from DNA to RNA to protein. And so RNA, how are the transcriptome, so how's the message moving through the sequence from DNA to RNA to protein. And this is an area we're working on at the moment, is looking at not the genetic code, but how the genetic code is being read. And so looking at individuals who've had corneal surgery, and instead of discarding the tissue which is removed, is donating the tissue for research, and then comparing the message in that tissue compared to control tissues, and looking at the difference in the way the message is being read. And if we can do that, you can then work back to the DNA code. And so a lot of changes, and looking at the most important ones. And so this is ongoing work, and you can provide these computerized derivatives of how one molecule or message relates to the other. Next slide, please, which looks a bit like the airline map of America. So you can get to different points on different airline routes. So it means there's lots of different ways that this message can be transmitted. Next slide, please. We do know there's a genetic effect. And so because only a small number of people have a known relative with keratoconus, that doesn't mean that it's not a genetic disease. What it does mean, or we think it means, is that it's a complex change. And so I think a simple analogy for this is that people traditionally think of a genetic disease as when you deal out a hand of cards, and if you have the king of diamonds, you have it, and if you don't have it in your hand, you haven't got it. So it relates on one card change in your pack. But a complex disease is that you have to have a royal flush in your hands. You have a sequence of cards, and that then determines whether you've got it. That is much more difficult to tease out the mechanism than working out why that individual's had the king of spades or diamonds in that. We have tried hard to collect families with this, and the best information is that it seems to be an autosomal dominant change, so it's on a gene which is not a sex chromosome. The evidence is that there's concordance in twins, and some of us, or you, will have participated in our twin study, where we collected 19 pairs of twins with keratoconus who were examined, and the individuals who were identical twins were much more likely to have similar corneal changes in each twin than twins which were not identical twins. And so similarity of the genetic information outweighs the environment, because twins were usually brought up in the same environment. And these family histories we've got here aren't going to provide the answer, but they're good validation sources. So we get clues and look if the segregation in the families, i.e. individuals with the change, which are coloured in black, do they have a change in, as compared to people who don't have keratoconus, who are the unaffected. So is it affected but not unaffected? So several large families we've collected are working for validation. Next slide, please. In the past, we've looked at the genetic studies. The linkage analysis is looking for a candidate genes, the conditions which are associated with keratoconus commonly, such as Leber's optic atrophy. Is there a gene close to that which is causing keratoconus? No. So that's been a dead end. For us, candidate gene studies, looking at enzymes which may contribute towards this, are these causative? Unfortunately, no. The main area of interest, which is our area, is what's called genetic genome-wide association studies. And so these are studies where you recruit a large number of individuals with keratoconus in this instance, and then compare as a group their genetic message with people who don't. And this is what we're doing, and so the target is to recruit 3,000 individuals with keratoconus and then compare their genetic message with 6,000 individuals who haven't. 3,000 seems huge, but we've got to 2,700 at the moment, so we're almost there. Looking at that comparison, it's an anonymized type of research, so it doesn't feed back. So any individual, any of those 3,000 individuals doesn't get a printout telling them what's going to happen. It's just all of the people with it compared to people who don't have it. Looking at these other studies, and so because it's much more difficult to fund this research in keratoconus as towards myopia, there are large studies in different parts of the world who are looking at other measurements of the eye to try and find out what controls eye development, such as white to white, which is the distance across the cornea, keratometry, which is a curvature of the cornea, anterior chamber depth, so the distance between the iris and the back of the cornea, and corneal thickness. And so large numbers, very big studies have been conducted on that. And so you've measured in the general population corneal curve and corneal thickness, but hang on a minute, corneal curve and corneal thickness are major risk factors for keratoconus. So is there any knock-on effect or result from that which can be helpful to us? Next slide, please. Just candidate gene approach. So this is the large number of things which are associated with keratoconus, neurofibromatosis, Leber's atrophy. So none of these have provided a uniform clue in the population to keratoconus. Next slide, please. Corneal thickness measurements. So looking at 20,000 individuals, normal individuals, and patients who are short-sighted, there's a very strong message that a gene called ZNF, cordon-like, this is corneal thickness, this gene here, ZNF469, and this one here, cordon-like 1, which is also associated with a condition of corneal thinning, gave very strong signals on that. And so corneal thinning in this condition here, which is called brittle X-linked megalocornea, again, didn't segregate. So this is the usefulness of our families in validating the results. Next slide, please. This is another one of the genes that came up in those studies. This is actually, brittle cornea syndrome here, which is an inherited disease where the cornea becomes extremely thin. Looks a bit like keratoconus, but isn't. The cornea is very fragile, and I'm sorry about this awful picture at the top here. The cornea is very susceptible to minor injuries, and the eye can rupture. But again, this gene was not related in the population with keratoconus. So again, clues, the rabbit is set off and it's being chased, but it's not validated in the populations. So next slide, please. In the population, this is a summary slide showing all the reported papers, and so each one of these little things here is a graphic of a chromosome, and so there are 22, and the red and the yellow and the green are papers which are reported associations with keratoconus, and the unifying thing is all these studies are too small. They're not powerful enough to give us good results. The second thing is that they're all scattered all over the genome, and so either it's an extremely complex condition, or else some of these are just wrong. They're not there. The studies were too small, and they're giving false information. Next slide, please. And so this is the approach that we've used, is measuring corneal thickness or corneal curvature. This is on 20,000 white and South Asian patients. This is called a Manhattan plot. So this is the signals throughout all the chromosomes, and then you look for signals which are increased. And the highest one here is ZNF469, so something markedly different in patients who have abnormalities in corneal thickness compared to those who don't. This is the gene which causes brittle cornea. Brittle cornea looks a bit like keratoconus, but with our family studies, any changes are not segregating. And so it may be related or must be related in some way, but it's not cause and effect. So how it's working, we don't know. And the study that we talked about at the beginning is looking at another study which was actually done in East Anglia, looking at corneal curvature. So corneal thickness is related to keratoconus, corneal curvature is also related to keratoconus, and there are a number of other genes which have lit up as being strongly associated with changes in curve. This is EPIC study in Norwich and East Anglia. And so what we wanted to do is to take those genes and look at them in a population with keratoconus. So this is what we were talking about in a moment. So this is a knock-on effect to population-based studies which have measured differences in parameters, in curve and thickness, and then we take those results and look at them to see how they relate to keratoconus. Next slide, please. So visual rehabilitation, very nice summary of how all the options with this. And so spectacles, contact lenses, surgery. What's missing down here is anticipation, is to identify individuals who are at risk of this. Monitor them, look for really early changes, and then either with cross-linking, prevent further deterioration, maintain vision when it's useful unaided or spectacle-corrected vision, or use this type of genetic research to develop treatments which are more sophisticated than that, to keep things from getting worse. Next slide. This is a summary slide. We know it's complex. Research may open other doors for better targeted treatment. Thank you. Next slide. None of this, I didn't do all this. There's a huge team backing all this throughout the world, collaborators, and these are the research group which supports it. Thank you.
Thanks very much for that. Very interesting presentations this morning. Technically, we're now going to lunch, but I'm quite happy for us to take 5 minutes or so if there are any burning questions people would like to raise now. So if there are, please put up your hands and we'll try and deal with those.
Just the first part, why do you still have to wear a contact lens after a corneal graft? So two issues with corneal graft surgery, which I hope were explained before you had your operation. There's the technical side of performing a transplant and having a transplant survive, which are those lines you saw, survival curves. That talks about success of a corneal graft is a sort of physically functioning bit of tissue. It doesn't address how well you see with that. And the issue of actually having useful vision from a corneal graft is sometimes actually more technically problematic than actually just doing it. And so we teach our fellows that actually just the function of doing a corneal graft is just the beginning. That they move on, they get their appointments, but we have to look years later with individuals who are struggling with contact lens fit, they can't see, they've got secondary complications and whatever. And so the reason is that the cornea is the major functioning focusing surface of the eye, and any small distortion of that will cause blurring of the image. And it's not possible to secure a graft with sutures and to take into account the irregular healing process at the interface. It's not possible to anticipate that to get a perfect functioning graft surface. Can't be done. So all patients should have been told that after a graft, approximately 50 to 60% will need glasses to achieve their best vision. The remainder will have useful vision, but better vision with a contact lens, and the chances of having driving vision unaided is probably less than 5%. So it's the unpredictable aspect of this is the healing and the shape of the cornea afterwards. So diet, second point, we all know that diet can affect allergy, and allergy can make contact lens wear worse, but I don't think any evidence exists for a role in, or nobody knows of, I'm not saying it doesn't exist, there isn't any, but nobody knows of any evidence of a role in diet in determining the onset or progression of keratoconus. I'll ask another pianist to answer that one.
That was neat, Steve. Seriously, though, training surgeons to do lengthy, complicated, diverse procedures like corneal transplantation, what I used to do was to encourage those learning to do a small part of the operation and then take over again. And as they developed in skills, dexterity, and thinking with their fingers, as I used to call it, then they could eventually take over and do an entire operation under supervision. And then there was another lengthy stage until they could do the same without supervision. So that's the normal procedure. Even such things as I mentioned, holding the tissue, putting the needle through to the right depth and making it come out at the right place. These may sound very straightforward, but they're by no means straightforward. And they can be taught, and they are taught. And that's how it's done. And they will play wrong notes to start with. But the piano teacher is there in the room watching and can put them right.
And there is, one lady here, if you can take her question.
There's quite a lot of research being done now in virtual reality and computerized programs, not so much for corneal surgery, and also people have developed forms of plastic to practice on. So there is work going on about that to try and refine skills before letting surgeons loose on patients. Yeah, I mean, there are sort of anecdotal reports suggesting, well, allergy, there's a gender bias, and keratoconus was thought to have a gender bias, but more recent larger population studies have gone to an interval of conflicting results, and probably no, but is the most recent data on that, in families where it seems to be one side or the other, as it may be chance.
A lot of work has been done on colour and contrast for visibility, and fortunately most computer operating system designers make it possible, as you say, to change the background and the colour of the screen. And in many cases, it's not one size fits all. It's a question of simply trying all the various options to see what suits you best. But there are no magic glasses. There's nothing else you can do in order to reduce the, I presume it's glare that you're complaining of, is it? Glare? Yes. So it's just a question of finding the best compromise for yourself.
I think we're just going to take one more question.
So Munson sign is, a historian would know when it was first described, who Munson was and whatever. It's a sign when you ask an individual with keratoconus to look downwards, and you can see that the lower lid is distorted by the protuberance of the cornea, so looking downwards. And it's a sign which dates back sort of when before the advent of these more subtle techniques. And so it's a thing which sort of medical students read about now, but almost never would we rely on it to make a diagnosis now of keratoconus. We've got much better methods for that. So it's physical distortion of the eyelids by the protuberance of the cornea, which would have to be advanced to be noticeable with the naked eye.